Hello friends, my name is Alpit and in today's class we will be discussing about what is topological sort and what are the use cases of it. So the first use case is, suppose if you are building an application. To build the application you need to first build all of its dependencies. For example, if you have an application A which has dependencies D1, D2, D3, D1 has further dependencies on D4, whereas D2 has dependencies on D4 as well as D5. Likewise, D3 has dependencies on D7 and D4 has dependencies on D6. So if you need to build an application A, first you need to build the dependencies which has no dependencies, for example D6, D5 and D7. Once these are built, then you can further build dependencies on items like D4, D2 and D3. Once those are built, then you can build dependencies D1 and D2, and once D1, D2, D3 all are built, then you can build your application. If you see the second use case, suppose if you are studying in an university and you want to take course C1, C2 or C3. So here if you see, there is a prerequisite course for C1 which is C4. To take the course C2, you need to first complete the course C4 and C5. And to complete the course C4, you need to complete course C6. So here if you see, if you need to perform a task or set of tasks, if those are having some dependencies, first you need to complete those dependencies, and that can be done in some order. Then you can actually complete the main problem. So to solve such problems or similar problems, we have topological sort algorithm. In topological sort algorithm, we use queue, which is a first in first out data structure. So to solve this application build problem, we have an adjacency list of this graph. In adjacency list, basically you have a key as the node and value as the list of the nodes which is connecting to that node. So here in our case, basically key is node A and the values of list of the nodes or the dependencies to complete this A. For example, if you see here, A has a dependency on D1, D2, D3. Likewise, D1 has dependency on D4. D2 has dependency on D4 and D5. D3 has dependency on D7 and D4 has dependency on D6. So as I told, we will be using queue to solve the problem using topological sort algorithm. So in topological sort, if you are not allowed to change the input data structure, then we need to create a two-dimensional matrix of n cross 2 size, where n is the number of nodes and the second column would have the number of dependencies it has. So if you see here, A being the node, it has dependencies on 3 items. D1 has a dependency on 1 item. D2, 2, D3, 1, D4, 1. And D6, D5, D7 has 0 dependencies. So it's basically D6, 0, D5, D7. So basically D6, D5, D7 can be pushed to the queue to be processed because they don't have any dependencies. So we'll start with a queue. So suppose this is our queue. So first what we do, we will process all the dependencies which has no dependencies. So here in our case, you will see D5, D6, D7 does not has any dependencies and can be processed in parallel or simultaneously. So you insert D5, D6, D7 to the queue. So this is a normal architecture where you have a queue and you have multiple workers, basically which are processing that queue. So as soon as they find any element in the queue, they process it. So here in our case, you build that dependency. So if an item is present in the queue, it means either it has no dependencies or all of its dependencies are resolved. So these workers will start processing D5, D6, D7. So let's suppose they picked up D5, D6 and D7. So what happens? Once D5 is going to be processed, they will go to the adjacency list and they will iterate through all the values of the entries, and any element, if D5 was the dependency count of that node will be decremented by 1. So here if you see, D5 was dependency for D2, so basically you decrement the dependency count for D2, which is 1. Further, if you see, D6 was the dependency for D4, so as you have completed D6, then D4 count will be decremented. So here what you do, as soon as you see that if the dependency count for a node is 0, it means right now it has no dependency and it can be processed. So as soon as it is 0, you put that element to the queue. Further, you see, like when you process D7, you found D3 was having dependency on D7, then you decremented the count for D3 in this 2D matrix, which is again 0. So now D3 has no dependency, it can be processed, so it will be pushed to the queue. So these workers, as soon as any items is pushed, they will start processing it, so that this D4 will be processed. So once D4 will be processed, D4 was dependency for both D1 and D2, so we'll go to the matrix and reduce the dependency count for D1 and D2, which it will be 0, and this is also 0. So once D4 is processed, you see D1 and D2 are ready to be processed, they don't have any dependency, so you will push D1 and D2 to the queue. Now these workers, as soon as they find something available to the queue, they will process it. So D3 will be processed. Once D3 is processed, you see D3 was dependency for A, so the dependency counter for A will be reduced by 1, so it will be 2. Now in parallel, D1 and D2 are also processed by any of the workers. So D1 and D2 are processed. Once D1 and D2 are processed, those were the dependency for A, so there will be 2 will be decremented to the dependency counter for A, so it will be 1 and 0, 1 for D2 and 1 for D1. So now you will see all the elements in the queue are processed, the queue is empty, so you will exit from your program, and then what happens, if you see, you have processed all the dependencies. So basically you have processed D5, then D6, D7. So basically D5, D6, D7 can be processed in parallel to have better time complexity. And then this is one of the ordering where you process D4, D3, D1 and D2. And once everything is processed, if you see, there are total 7 direct or indirect dependencies of A, and these all 7 are processed, then you can build your application. So this is one of the classical example for topological sort algorithm, where you can use the algorithm to solve or process the dependencies and then actually solve the main problem. Another optimization you can do here is, if you see, every time you process any element or dependencies, you need to iterate through all the entries of adjacency list, checking if anyone has a dependency on that item. You basically decrement their counter, dependency counter. But if you have another map where you can keep track of every node and all having dependency on that node, then you may not require to iterate through every item in the adjacency list. For example, you can create a map where you say D6 is the dependency for D4. D4 is the dependency for D1 and D2. And then you can say D7 is a dependency for D3. Likewise, you can say D3 is dependency for A, and then D2 has a dependency for A, and D1 has dependency for A. So what happens anytime you process any element? For example, if you have processed D4, so when you process D4, you don't need to go through all the items in the adjacency list, so that you know if someone was depending on D4, you need to decrement the counter. You can look up in this map and you say, okay, D4 was the only dependency for D1 and D2, so that you can directly go to D1 and D2 and decrement the counter. And if same thing, if that goes to 0, then that item is available to be processed and you push it to the queue. So that's an additional level of optimization you can do. Obviously it comes with more space and more pre-processing, so that can be done as part of optimizing the time complexity. So in today's class we understood what is topological sort and what are the use cases of it.